Hi Math Dragons, it's me, Mrs. Morgan, your instructor. Earlier today we looked at Lesson 5, Composing and Decomposing Numbers. We talked about how to make factor trees by chopping up numbers into their factors until you come all the way down to prime numbers, which is called prime factorization. Many of us explored the bead problem, and some classes made it as far as calculating the greatest common factor using prime factorization. Homework this evening was activity 5.2. Now you can solve these problems with or without factor trees. And in fact, only one of them did I attempt the factor tree method. So I want you to feel empowered to try any method that makes sense to you. I did want to give you assistance with the problems since they're very wordy. I wanted to give you clues and hints on where to go. So I actually already took the time to work these problems out, and I'll show you my work in this video. Most of this vocabulary should feel familiar at this point. Remember that common factors help you think about how to divide or share things equally. Remember, factors are like chop chop, ninja chop. Common multiples help you think about how things with different cycles can occur at the same time. So multiples, I think multiply, I think increasing. Number 1. Ramon and Justine are watching different broadcasts of a parade on television. The broadcast Ramon is watching airs commercials every 17 minutes. That's an odd number to be working with. That was the first thing my brain said. The broadcast Justine is watching airs commercials every 14 minutes. Both broadcasts started at 7 a.m. and are scheduled to end at 9 a.m. This is actually really important information. That's only 2 hours that this can even happen because they're watching a parade. When will commercials air on both broadcasts at the same time? This one happens every 17. This happens every 14. It's going to continue to happen. So you have to ask yourself, are you looking for common factors where we would chop up the minutes, or are we looking for common multiples where we're going to skip count the minutes? You should have said skip count. If you did, be very proud of your answer. Now here's the work I did for this one. I know the broadcast is from 7 a.m. to 9 a.m. So it's only 2 hours long, which is 120 minutes. We often wonder, if I skip count, if I'm looking for that least common multiple, how do I know when to stop? My normal answer would be stop when there is a match. Unfortunately, this one's going to be really long, but I don't need to actually wait that long because 120 minutes would be here, and the broadcast ends at 9 a.m. There's no match here, and then I did this one, and once 120 minutes came to with this commercial that runs every 14 minutes, this broadcast would be over. So after 120 minutes, both of these parades are over. And during those 2 hours, there's never a repeat. There's no match. The commercials will never air on both broadcasts at the same time. So that was kind of a sneaky question. I don't know. Don't usually see those kind. Next one. 2 cyclists ride on the same circular path. The first rider completes a lap in 12 minutes. The second rider completes a lap in 18 minutes. Both riders start at the starting line at the same time and go in the same direction. If the riders maintain their speed, after how many minutes will they meet again at the starting line? Explain your reasoning. I felt this one was pretty straightforward. You've got 2 riders. One's going a little faster than the other. So I went ahead and showed that work here. Rider number 1, rider number 2. This rider does a lap every 12 minutes. So first lap, second lap, third, fourth, fifth, sixth, seventh, eighth, ninth, so on. This rider takes 18 minutes to go a lap. So first lap, second lap. Well, they end up at the same place, like if you were thinking about like a track. Rider number 1, if this is your starting line, goes 1, 2, 3 laps in 36. And then rider number 2 will go 1, 2 laps in 36 minutes. But either way, they're stopping here. So in 36 minutes, they're at the same place. This is first rider's third lap. and this is the second rider's second lap. But in 36 minutes, it's a match. That's how you accomplish and solve question 2. Number 3, Dr. Abramson and her assistants are working on 3 different experiments using water. Each experiment lasts for 15 minutes. For the first experiment, the water level must be checked every 12 seconds. For the second experiment, the temperature of the water must be checked every 30 seconds. For the third experiment, the color of the water must be checked every 36 seconds. In minutes, list the time all 3 experiments will need to be checked at the same time. Take note that there is a 15-minute time limit. You're not going to go beyond 15 minutes. Anything beyond that is extraneous. This one's experiment is going to need to be checked 12 seconds, this one's 30 seconds, and this one's 36 seconds. Are you going to chop it up, or are you going to look for multiples? These are your 2 choices. When it's time, you tend to be looking for multiples, and we are going to be looking for multiples here. Here's my work for number 3. 15 minutes total, so that kind of gives me an ending point. I don't need to go more than 15 minutes no matter what I do. Seconds were a bit to work with because I'm going to be converting seconds to minutes. You just need to remember that every 60 seconds is a minute. I started to make little side notes here. So here's the first experiment that needs to be checked every 12 seconds. I made a big long list. And to be truthful, my list originally stopped here. I was like, oh, 120, that should be good. Then I started to make this list. And I was like, okay, 120, but I'm going to go a little further. And this is when I got worried. When I started to make this list, and, I made a little mistake. I got to 180, but my other list hadn't gotten to 180 yet. So I needed to go back to my original list until I matched something. I wasn't matching yet. And then finally, once I reached 180 down in the 12s and had a match with the other 2, I was good. Well, 180, if you don't know, is equivalent to 3 minutes. 60, 60, 60. So in 3 minutes, all 3 experiments need to be checked. Well, that means in another 3 minutes, they need to be checked again. And then another 3 minutes, and then another 3 minutes, and then another 3 minutes. So at 3 minutes, 6 minutes, 9, 12, and 15, that is when all 3 experiments are going to be checked at the same time. So once you have the first 3 minutes, you can just do multiples of 3, because you know they're going to match again every 3 minutes. You're doing good. We're almost through. The students in Mr. Michael's art class are decorating a booth for Harvest Day. They have blue cloth that is 60 inches long, gold cloth that is 48 inches long, and white cloth that is 72 inches long. They want to cut all the cloth into pieces of equal length. What is the greatest possible length of the pieces without having any cloth left over? When I see greatest, I start to ask myself, could it be a greatest common factor? And then they were saying that we need to cut the cloth, and I was like, cut, chop, okay, we must be dealing with factors. You can totally do a factor rainbow here, if that is the route you go. But I was feeling fancy, and I tried the factor trees. So you know this is not a strength of mine. I don't often use the factor trees, but I did, like the book taught us to do, in 5.1 and in, I think, lesson 4.2. I organized my prime factorization. So I took the prime factorization and put it in a table. Took the one from 60, put it in my table. Took the one from 72 and stuck it in my table. I carefully lined up how I wanted things to be. Like I knew there wasn't a third match here, so I left that blank like they did in the Carnegie textbook. I knew there wasn't a match here, so these 2 were blank, and so on and so forth. And then I looked for triple matches. I have a triple match here, here, and here. I remember the book telling me to multiply all the common factors together to get the GCF. So that's 2 times 2 times 3, which gets me 12. So that means the greatest common factor is 12. Now, if you tried the rainbow method and got 12, I'm thrilled, because that means we're getting the same answer. So part A is asking, what is the greatest possible length without any cloth left over? 12 inches. 12 inches is the greatest possible length. What to do from there? I'm going to put a label on that for you. Is how many pieces from each cloth will you get? So if you take 48 inches and divide it by 12 inches, you're going to get 4 pieces of gold cloth. 60 inches divided by 12 inch pieces, you're going to end up with 5 blue pieces and then 6 white pieces. So this is your answer for B. One more question. I actually felt like they saved the easiest for last. Boxes that are 16 inches tall are being stacked next to boxes that are 20 inches tall. What is the shortest height at which the two stacks will be the same height? Well, they're stacking them. So it's like this repeated process going on. So I'm imagining it's going up, 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 taller. Well, things that go up, up, up are multiples. So that is exactly what I did. I had the 16-inch box, and I skip counted by 16, 32, 48, 64, 80. And I had my 20-inch box, and I skip counted until there was a match. So at 80 inches in height, the boxes will be stacked at the same height. Part B asks, how many boxes will be in each stack? Well, this was 1 box, 2 box, 3 box, 4 box, 5 box. At 5 boxes, I'm 80 inches high. However, this box starts out bigger. So 1, 2, 3, at 4 boxes, I'm 80 inches high. So you need 5 of the 16 inches box and 4 of the 20-inch box to be at the same height. I was thinking maybe a little sketch would help you. So if I have the 4, those are the 20-inch boxes, but then you know you need to be the same height, but only be 5 boxes high. So this is 16, 16, 16, 16, 16, whereas this is 20, 20, 20, 20. But the height of both stacks is 80 inches. So here you're dealing with multiples again. Just to recap all the work we did. Number 1, they were looking for multiples. Number 2, more multiples. Number 3, more multiples and more complicated because you had to convert between seconds and minutes. Number 4 was our greatest common factor. And number 5, more multiples. So that was a heavy multiple lesson. You should be all set. Tomorrow we will work on 5.3 together in class. You'll go home with a review worksheet because the unit test is Friday. Thank you, Dragons.